Dividing complex numbers in their exponential form also observes a rule in the laws of exponents. Find it out here in Mathematics of Engineering. With the exponential form of complex numbers as z, which is equal to r times e raised to y times theta, division of two different complex numbers would look like z1 all over z2. Note that the moduli can be directly divided, but the quotient of e having similar base follow the quotient rule, which states that e raised to a all over the same base e raised to b will be e raised to the difference of the exponents a and b. Let's discuss the procedure in detail through an example. We are to look for the ratios of z1 over z2 and vice versa of the two given complex numbers, graph the outcomes, and convert the same in Cartesian forms. Let's start with z1 over z2. That is 4e raised to y times 5 pi over 4 all over z2, which is 5e raised to y times 7 pi all over 12. The modulus can be simplified directly as z1 over z2. That is 4 all over 5 or 0.8. For the quotient of e's, we are to subtract the exponents as the base is the same for both terms. So we get e raised to y times the difference of 5 pi over 4 and 7 pi all over 12. Having two different denominators, we take the LCD to unify the fractions. The LCD for 4 and 12 is 12, so the equivalent fraction of the first term is 15 pi over 12. This is subtracted by 7 pi over 12 to have 8 pi all over 12. Reducing the fraction, we get the simplified e term as e raised to y times 2/3 of pi. Graph the moduli and argument to see that the vector lies in the second quadrant, and the exponential form is 0.8 times e raised to y times 2 pi all over 3. With the exponential form already determined, convert this into polar form, which becomes 0.8 times cosine of 2 pi over 3 plus I times sine of 2/3 of pi. It is from here that we take the Cartesian form by simply multiplying 0.8 with cosine of 2 pi over 3 to get negative 2/5, and 0.8 times sine of 2 pi over 3 as positive 2 root of 3 over 5 times I. In decimal form, z is negative 0.4 plus 0.6928 I. If you are hesitant to use the polar form in taking the Cartesian form of the complex number, we can simply take the components of the vector. The real number is solved as a, which is 0.8 cosine of 2 pi over 3, giving negative 2/5. The imaginary number is taken as 0.8 sine of 2 pi over 3, and that is 2 root of 3 over 5. So z is negative 2/5 plus 2 root of 3/5 of I. In decimal form, we get negative 0.4 plus 0.6928 I. Next is to take z2 over z1, that is 5e raised to y times 7 pi over 12 all over 4e raised to y times 5 pi over 4. The modulus is solved as 5 over 4 giving 1.25. The other part is then divided, but with the same base, we take the exponent as 7 pi over 12 less 5 pi over 4. We again take the LCD to arrive at 7 pi over 12 minus 15 pi over 12, which results to negative 8 pi over 12, or simply e raised to y times negative 2 pi over 3. The negative sign of the argument means that the rotation was clockwise, which leads the vector to the third quadrant, still with r or length of 1.25. To make the argument positive, take the counterclockwise angle, which is 4/3 of pi. So we write z as 1.25 e raised to y times 4 pi over 3. To take the Cartesian form, it is easier when a complex number is converted to its polar form and simplified. In its polar form, z is 1.25 times cosine of 4 pi over 3 plus I times sine of 4/3 of pi. Now take 1.25 times cosine of 4 pi over 3, which gives negative 5/8. Then 1.25 times I sine of 4/3 pi is negative 5 root of 3I over 8. In decimals, we get negative 0.625 minus 1.0825I.